MSG, Multi-Stream Generative Policies for Sample-Efficient Robotic Manipulation. Generative models such as flow matching are powerful and flexible robot policies. However, when it comes to policy learning, they're not sample efficient, but typically require in the order of 100 demonstrations. To tackle this issue, we proposed the Multi-Stream Generative Policy, MSG, an inference-time composition framework that trains multiple object-centric policies and combines them in inference time to improve generalization and sample efficiency. MSG is model agnostic and inference time only, hence widely applicable to various generative policies and training paradigms, such as diffusion or flow matching. MSG learns high-quality generative policies from as few as 5 to 10 demonstrations. Its modularity further enables zero-shot transfer to new and cluttered scenes. To understand how MSG works, consider the example task of opening a microwave. Given a set of demonstrations, we model the end effector trajectory in multiple coordinate frames. In this case, the initial end effector frame and the microwave's frame. These two local models, or streams, complement each other by being precise in different parts of the trajectory. Therefore, composing them at inference time leads to a joint model that is precise throughout the trajectory. Such multi-stream learning is a proven technique for probabilistic policies like Gaussian mixture models. How can we apply it to generative policies? We present two versions of MSG. The first is a simple black box solution of ensembling the local models. We let the models make their predictions and then combine them using a weighted average. The weighting can take into account the relative certainty of the predictions, and we will discuss it in detail in just a minute. While the ensembling is very simple to implement and surprisingly effective, it has its limitations. Consider this toy example of composing the red and blue distributions, with the green circle indicating the models prior. For the unimodal distribution, ensembling works fine. However, it fails in the multimodal case because it lacks a mechanism to ensure that all models converge to the same mode. A more powerful approach that resolves this issue is flow composition. Generative models like flow matching typically do not predict actions in a single step. Instead, they predict a vector field that iteratively refines an initial sample. By composing the predicted vector fields instead of the final actions, we encourage the local models to converge to a common mode. Using a Markov chain Monte Carlo sampling scheme further improves flow composition. Both ensembling and flow composition rely on weighting the local models. We propose and investigate 3 different weighting strategies. A surprisingly effective approach is to use a simple progress-based schedule to weight the models. Yet these schedules are hand-designed and require a priori knowledge of which models matter when and where. Instead, we can also train the models to estimate their own certainty using the variance observed in the training set. At inference, we then use the predicted certainty to weight the models. This empirical approach does not require privileged information and allows us to learn task-specific schedules. However, it requires modifying the model to add certainty estimates. Our final approach is also variance-based, but it does not require altering the model. Instead, per model, we sample multiple particles in parallel and compute the model's weight based on the empirical variance of these particles. This parallel sampling faithfully reconstructs the variance-based schedules without augmenting the learning problem. We now show qualitative examples of policy execution, both in simulation and in the real world. All shown policies were trained using 10 demonstrations. From such little data, MSG achieves robust performance, both on single and multi-object tasks, even when high precision is required. For example, when opening a microwave, hanging a mug, or inserting a peg. In contrast, single-stream approaches such as ACPL or global frame flow matching struggle with sample efficiency and high precision requirements. For instance, they often fail at peg insertion and mug hanging. And when opening a door or drawer, they frequently slip off the handle. Our experiments on a real Franca-Amica robot confirm these results. MSG achieves the high precision needed for successful manipulation of objects, be it in single object tasks, like opening a drawer, or in multi-object tasks, like pick and place. Again, MSG's performance is in stark contrast to single-stream approaches, particularly if the variance between task instances is large. In our real-world experiments, we use a dyno-based keypoint predictor to identify object frames. Other visual models, like foundation pose, can be used with MSG just as well. Such a modular approach has the additional benefit of enabling zero-shot policy generalization. For example, Dyno enabled zero-shot transfer to new and cluttered scenes, as shown here. Thank you for watching. You can find code and more information at our project website.